I've had this muted the entire time. I've had this mic muted the entire time. No, we're not. I just realized I did not mean to press the mute button.
Was it muted the whole last video too?
No.
Okay.
No.
That would be real bad.
Okay, so we just seen how positive displacement works. I cannot believe that I did that. Like, I'm about to cry. But thank God it was just me reading the definitions. Basically what you've missed, if you didn't hear a word that I said, was I read through every single definition in the book for all these pumps that we're having to learn about. And now we're trying to look up examples of them so we can actually see what they look like and what they are, what they look like working in hydraulic systems. Okay, fixed displacement pump. Fixed displacement pump. Search. Alright, so that's what it looks like. Cool. Now let me see if I can find a video. Fixed displacement piston pump.
That look. That look is a look that can only happen by a roaring fire at a...
The device we're going to describe here can also be used as a hydraulic motor. A main shaft connected to a gasoline engine or an electric motor rotates a cylinder barrel. The cylinder barrel looks like a revolver's barrel, and the pistons are located inside this barrel, just like bullets. The rotation of the barrel forces the pistons to rotate with the barrel. The round ends of the pistons are connected to the yellow shoes, which slide on an inclined black swash plate. Springs in the cylinder barrel, which are not shown in this animation, forces the pistons towards the swash plate. Let's observe the motion of one piston inside the cylinder barrel. Notice that during one revolution, the piston moves inside the cylinder barrel from the top left to the bottom right, and back to the starting point. The horizontal distance between the top left and bottom right are fixed, and thus the name of the pump, fixed displacement pump, is derived from this fact. While the round end of the piston rests on the yellow shoe, which is sliding on the black swash plate, the other end moves closer to the green port plate during half of the rotation, and moves away from the green port plate during the other half of the rotation. The view of this port plate is shown as if an observer is looking at the pump parallel to the rotating shaft from the yellow port location. As you can see, there are two crescent-shaped gaps on this plate that are shown by the red and blue colors. The red indicates the high-pressured oil, and the blue indicates the low-pressured oil. The same color convention is true for the oil inside the cylinder. Notice that for the high-pressured oil, the pistons move toward the port plate and force the hydraulic oil into the red crescent gap on the port plate. The movement of the oil in the crescent is shown with the white bubbles. For high-pressured oil, the bubbles move toward the exit port, indicating that the oil is coming from the cylinders. For low-pressured oil, the bubbles move away from the inlet port, indicating that the oil is coming from the outside. The oil in the blue crescent is sucked in by the pistons moving away from the port plate. After a cylinder reaches its furthest point from the port plate, the cylinder passes the gap between the crescents and the compression cycle starts. Let's see how two pistons operate. Notice that during compression, the piston passes in front of the shaft.
Alright, we get the idea, right?
And while replenishing with...
Cool.
Kind of just feel like they said the same thing multiple times.
Yeah, that's what I'm thinking. Alright, so variable displacement pumps. And once we get through with this, we're going to go to chapter 9, like the pressure control and stuff, okay?
Okay, there was something that just popped in my head, like, on my way here. Is the hydraulic stuff and pneumatic stuff interchangeable, or?
I don't think so. I don't think so.
I didn't think so because they would have to use different seals at least.
Right. I don't think they are. So this is a variable displacement piston pump. Is that what we just looked up?
I thought we were looking at fixed earlier. No, this is different.
Okay, so maybe I need to go back a little. Okay, so this is what Robbie was talking to me about the other day. Once that flow gets to a certain point, that plate will move. So, depending on what type of pump it is, see how it would go from side to side? That means that it's changing flow. And that's true for valves as well. Because like it's putting pressure on that plate until like say like 900 psi, and then it straightens out so no more pressure can push on it. So it can't create any more pressure. That's what that trainer does. All right. Pneumatic systems, enter. Alright, so I looked it up, Dylan, what your question was. I used the Google. And it says, similarities of the two are many. They both function in a very similar fashion, just with a different means of movement. Both hydraulics and pneumatics require similar components, and the idea behind them both is that force is exerted, resulting in the ability to do something, such as living, spinning, moving, pushing. So they are very similar. I don't know if that even answers your question, but
Yeah, I mean it does to an extent.
okay.
Because I know, like, when you move from fluid to air, bare minimum, they have to have different seals.
Mm-hmm. Yeah, because one is a solid, one is a gas, so.
How long was the liquid?
I said solid. For example, gear pump using. Alright, we don't have to look at what a gear pump is. External gear pumps. Let me just look up how do pumps work in a hydraulic system instead of looking up how do pumps work in a hydraulic system. Because I want to see like some of these systems these pumps are actually in. Do y'all not want to?
I sure do.
I know you do. Hydraulic pump types and how are they work. We're not watching that one. They can't even spell how do they work.
That's like 13 minutes. So.
Yeah, what are hydraulic pumps? Hydraulic pump, hashtag pump. Let's watch this 4-minute one and see what it's talking about.
Hey guys, welcome to SkillLink. Our body is a complex system of various components or organs working together. But the heart has got a unique place in this system because it circulates the blood which keeps the organs working. Similar to the human heart, a hydraulic system also has a heart that plays a unique role and powers the whole system. Wonder what that is? Yes, it's the pump. A pump is used in a hydraulic system to convert mechanical power into hydraulic energy. The main purpose of a pump is to produce the flow by taking the oil from the tank and delivering it to the rest of the system. When the hydraulic system resists the flow developed by the pump, then pressure is developed in the system. A pump is accompanied by an electric motor that delivers the mechanical power to the pump. Due to this, a partial vacuum is created at the inlet of the pump, which causes the hydraulic fluid to move through the pump. After the hydraulic fluid or oil is drawn into the pump, it is pushed into the hydraulic system, thus creating a flow of oil and transferring power to the system. In a hydraulic circuit, a pump is represented by the symbol where the arrowhead shows the direction of flow. In the fluid power industry, pumps are classified into two broad categories of non-positive and positive displacement pumps. Non-positive displacement pumps, also called hydrodynamic pumps, use the motion of the flowing fluid to maintain the pressure in the system. Non-positive displacement pumps work based on Newton's first law of motion. As the fluid is drawn into the pumping chamber, the action of mechanical drive causes it to speed up. This increase in velocity helps the fluid to move against the resistance of the system. The flow of fluid is responsible for the pressure generated in the system. Thus, hydrodynamic pumps are primarily used for transporting fluid from one location to the other. Such pumps are not capable of withstanding high pressure and are used in the systems with low pressure and high volume requirement. The most common type of hydrodynamic pump is a centrifugal pump. These pumps have a few moving parts due to which they are less costly and are easy in maintenance as well. Now let's move on to the next type, which is the positive displacement pump. They are also called hydrostatic pumps and are extensively used in the fluid power industry. The reason for this is that these pumps are capable of overcoming the load of the hydraulic system. As opposed to the hydrodynamic pumps, the positive displacement pumps are used where pressure is the primary system requirement. Hydrostatic pumps have a pumping element that expands and contracts in each pumping cycle. This pumping action first causes the fluid to expand into the chamber, and when the contraction happens, the fluid is expelled into the hydraulic system. One point to be noted for positive displacement pumps is that the fluid enters and leaves the pump at the same velocity. This means that the pressure in the system is increased by increasing the pressure of the pumping chamber. Another thing to be noted is that the volume of the fluid displaced by such pumps is dependent on the number of cycles made by the pump per unit time. The gear, vane and piston pumps are some examples of positive displacement pumps. When compared to non-positive displacement pumps, positive displacement pumps are small and have higher volumetric efficiency, which also provides greater flexibility in performance under varying speeds and pressure requirements. Well, that's all about the introduction to hydraulic pumps. We will be discussing the types and classification.
Okay, so that described it a little bit better, didn't it? Alright, I'm just going to give y'all a quiz on the pumps, open book, instead of having to watch every single pump. We get the gist of pumps. Like, they're the heart of a hydraulic system, right? So we understand that aspect. So let's move on to chapter 9, okay? We're going to go over these valves, because valves are a little bit more important to what we're doing anyways on the trainer. Would y'all not agree?
I agree.
Alright. So, let's go over what these valves do. Okay, so a direct acting pressure control valve is a valve that senses pressure through an internal pilot line connected to the inlet or the outlet of the valve in order to direct fluid flow to the bottom of its spool where it works against a biasing spring. So, let's see. A direct acting relief valve is a normally closed hydraulic system safety valve that sets the maximum system pressure and must be capable of allowing full pump flow through the reservoir. A direct acting relief valve is often located within 6 feet or less of the hydraulic pump. Per OSHA regulations, there must never be any other components connected to a hydraulic system between the pump and its relief valve. So, let's see. Let me start looking up stuff while we go over this. This isn't a very long chapter, though. So, this won't take us too long. Alright, let me pull up my slideshow I have for you guys for hydraulics too. So while we're going over these symbols, we can see what the actual valves do. Double clap. That's hydraulics. Now Ashley helped me make this symbol slideshow. So, and I'm gonna upload this to Canvas after we're done. And this would be just like the slideshow based what your quiz will be based off of. So if you literally just look at this slideshow and study it, you'll be able to make an easy 100 on the quiz, okay? So, pressure compensated pump. That's that symbol. Load sensing pump and fixed displacement pump. So we've already talked about all of them type of pumps. Obviously the M stands for electric motor. So let's see. So the pilot operated relief valve. All right. Pilot operated relief valve. Let's see if I can find that in the book. Y'all remember seeing that in your book? Yep, right there. I was going to say, I didn't remember what page it was on, but I knew I seen it. It's on page 280. So a pilot operated relief valve is a type of pilot operated pressure control valve that is used to control the maximum pressure in a hydraulic system. Pilot operated relief valves are used instead of direct acting relief valves when more energy efficiency is required. They also have a quicker reaction time and can withstand a larger range of pressure. Pilot operated relief valves are used in applications such as cranes, presses, excavation equipment, welding machines, and pipe benders. Pilot operated relief valves are sometimes called compound two-stage relief valves. They consist of a main spool and adjustable pilot valve that are both internal to the main valve body. So this is basically saying that it's used in bigger hydraulic systems. So that's what you would see in bigger equipment. All right. The direct acting pressure relief valve. Let me find what page that's on. If there's even a page, there we go. It's on page 266. We're going to be kind of hopping around here. It is a normally closed hydraulic system safety valve that sets the maximum system pressure and must be capable of allowing full pump flow through to the reservoir. So, that's basically like that's your safety, kind of. So, pressure at the inlet port of a direct acting relief valve is used to overcome the force of the biasing spring. Direct acting relief valves are always attached to a pump in parallel because when the valve is actuated, hydraulic fluid flows through it to the reservoir. So that's that symbol. Direct acting pressure relief valve. Pressure reducing valve. Wait, let's go over sequence valve first because I'm right here on this page. 267. Is a normally closed pressure control valve that makes various operations occur in an orderly manner, which you can kind of figure out this stuff by reading the name sequence. So, a sequence valve uses increasing pressure levels to actuate operations one after another. The sequence valve is installed in a hydraulic system when one operation needs to begin after another has finished. So you can kind of think of that as like, once we get flow to this valve, we need this valve to push flow to that valve. All right. Solenoid operated directional control valve. I'm not sure if that's in the book. Do y'all remember seeing that in the book? I didn't see that in the book, but I could be wrong. That might just be on the hydraulic trainer. All right. All right. Well, that's just on the hydraulic trainer. You might see that in some of your labs, but you may not. So we just won't worry about that. All right. Let's go over the brake valve. A brake valve is a normally closed, I'm on 278, is a normally closed pressure control valve that prevents a hydraulic motor from running away or speeding out of control. A brake valve has both internal pilot lines and remote lines for controlling the speed of the motors in a hydraulic system. A low setting allows the motor to start at a lower pressure and is controlled by the external pilot line connected to the inlet side of the motor. Because the brake valve is closed, the motor cannot rotate and pressure builds up in the pressure line to the motor. Once the valve opens, the motor begins to rotate. This constant opening and closing of the brake valve prevents the motor from running away. So that's a counterbalance valve, which is also a brake valve. And y'all know what the cylinders are. I mean, we've already done a few labs in there, and you know what the cylinders do.
You kind of look at it and know the difference between a single
Yeah.
and a double.
Yeah, I mean, it's pretty self-explanatory. I don't want to, like, babysit it too much. So, a needle valve. Pressure compensated. Let's see. I don't even know if that's in the book either. We're about to just all right. Let's see here. Y'all both done like the first few labs, right? Have you done any labs, Houston? On the hydraulic trainer? Yeah, okay. We're gonna have to hit the ground rolling this week because, like, for people who started it last week, what the labs are gonna be this upcoming week is we're gonna try to add like 3 or 4 every week, but they're not like, it's gonna take you like maybe 5 minutes to do the first lab.
Yeah, I saw that.
So
Lab one was due today.
yeah, but it's okay. Like, you didn't know because I had told you we didn't know when we was gonna get the trainer, so you can catch up this week. Like, and it's not gonna take you a long time to catch up. Like,
Yeah, you can kind of look at them like.
so basically what's going to be due this week is, for anybody catching up, it's going to be like activities 1 through 6. But that sounds like a lot, but it's really not. Like, this first activity, you're literally running 2 hoses. That's it. So, I mean, it's not hard. And so, let's see. Yeah, I got off on the wrong thing. Ashley, didn't we say that the needle valve was like the flow control valve? So, like, that's what you would. I'm trying to look at these schematics just so I don't describe it wrong, but that needle valve that you see right there is basically a flow control valve. And we're about to look it up on the internet because I don't have a good way of showing y'all the like book while I'm talking about stuff. That's why I'm relying so heavily on the internet. But next week I'm gonna have like my iPad or Robbie's, and that way I can actually like draw stuff out while I'm talking to y'all, so it's not like so weird me just sitting here reading all the book. So so that's a needle valve, and it's used to accurately control flow rates of clean gases or fluids. I was hoping we could have a video here. But obviously, that's what's inside of a needle valve. So it's literally just controlling flow. Like, you would twist it up if you wanted flow to be able to go through there, and you twist it all the way down if you don't want there to be no flow. So that's how you control flow of your fluid. Let's see. Which I don't understand why there's like a needle valve and all these different control flow valves and stuff. It kind of gets confusing, doesn't it? Because there's also a flow control valve. So
That needle valve don't look any different than a little cutoff.
Which one
basically what it is.
seeing now out of those? Are they pretty much all the same?
I mean, like, the needle valve is what you would connect to for pretty much every lab, correct, Ashley? You go into that first needle valve for every lab. So that's one you would be seeing. So this is the one you need to be concerned with right here. That right there. We put the more advanced symbols on here too, but they'll be like in the super later labs. Like, this is nothing you're going to see within the first couple of labs. Yeah, like. And then, so let's see, flow, how to flow control valves work.
An easier way to study hard is here with Bartleby Learn. Bartleby offers unlimited access.
Mechanisms by Mekanis Muller. Come to the video tutorials of mechanisms by Mekanis Muller.
Let's turn on the
In my
first
previous
guy.
video, the working principles of a needle valve has been explained.
We're gonna turn him off.
One of the biggest
That it restricts the flow rate in both directions. When you use a needle valve for speed control of a piston of an air cylinder in forward motion, it will also restrict piston motion in return stroke. You can solve this problem by adding a quick exhaust. Why are we talking about air? I mean, I guess we need to talk about that too. Flow control valves. But you get the gist of what a flow control valve does. It cuts off flow. If you want more flow, you twist it up. If you want to reduce flow, you twist it down, and it literally just cuts off flow. So twist that up, twist that down.
Until now, I thought you were moving the mouse.
No.
What's it called? Oh, okay.
Even on the other one where you was looking at that pump,
Mm-hmm.
the variable pump, and they were moving it at the top. I'm like, oh,
Do you understand? Do y'all understand what a flow control valve does?
yeah.
What does the green represent? Is that
I think that's representing air,
air? And then the blue represents
hydraulic fluid, I guess.
I was thinking
Because this is showing both pneumatic and hydraulic fluid. So, alright, now let's go back to the PowerPoint. Pressure compensated flow control valve. So let's look up how do restrictor valves work.
So the pressure, that last one.
The one we just went over, the needle
Also got a
valve.
Needle valve?
Needle valve is a flow control valve, like.
Okay. Because in the diagram, it has the little symbol for a needle valve.
Yeah, and that's why it's saying for every hydraulic lab you do, you need to run it to that needle valve, because that's how you can, when you reduce it over here, you see it in the flow tanks go up. So then if you pressurize it over here, the flow tanks go down. We seen that last week in the lab, and we'll catch you up, Houston, whichever day you come. It's not hard. So,
You can come with me tomorrow.
how one-way restrictors work.
a little weird anyway.
It's okay. I'm just trying to make friends. I don't have anything.
You'll be here Wednesday?
Restrictor valve.
I don't know.
How do restrictor valves work?
Well, I'll be here Wednesday.
My friends let me work overtime.
Flow restrictors. Here is a general video. Let's watch this one and see what it has to say.
Oh my gosh, Ryan Reynolds.
We get to see him again. Isn't that crazy?
I brought in one of our first and oldest customers was
Skip ads. Please don't be a robot. Super awesome.
This is a quick introduction to flow control valves, a little bit about what they are, different types, how they work, where they're used. We'll start with some symbols. So this is a classic adjustable orifice, so we've just got a normal orifice that we can change, shown adjustable by the arrow. And another common one is a pressure compensated flow controller. So we've got a little arrow that shows it's pressure compensated. We've got a sharp edged orifice which should give better control for against temperature of the orifice. Now, one thing with basic orifice, adjustable orifice here, design, got to adjust restricting in one direction only. So if we look at what they look like, this is our potentially our adjustable orifice.
I don't like him.
So the setting.
I do not like him at all.
This course is designed to give you an understanding of the basic concept of
Oh, silly.
She looks like she knows a lot.
flow or the pressure level. One misconception has been that pressure may be controlled with an orifice or flow control device. This is never accomplished with any degree of accuracy. For accurate control of force, 6 types of pressure controls have been developed. They are relief valve, unloading valve, sequence valve, reducing valve, counterbalance valve, and brake valve. By symbol, these valves closely resemble one another. Often, only their location in the hydraulic circuit will designate what type of pressure valve they are. Maximum system pressure can be controlled with the use of a normally closed pressure valve. With the primary port of the valve connected to a system pressure and the secondary port connected to tank, the poppet is actuated by a predetermined pressure level, at which point primary and secondary passages are connected and flow is diverted to the tank. This type of pressure control is known as a relief valve. A direct-acting relief valve is one in which the poppet is held closed by direct force of a mechanical spring, which is usually adjustable. Spring tension is set on the knob to keep the poppet closed until system pressure working against the poppet reaches the desired cracking pressure. When the system pressure reaches full relief value, all fluid is passed across the poppet to the tank passage. It should be noted that direct-acting relief valves are usually available in only relatively small sizes because it is difficult to design a strong enough spring to keep the poppet closed at high pressure and high flow. Pilot-operated relief valves are designed to accommodate higher pressures with higher flows being confined to smaller frame size than a direct-acting relief valve with the same rated flow capacity. The valve is built in 2 stages. The second stage includes the main spool, held in a normally closed position by a light, non-adjustable spring. The second stage is large enough to handle the maximum flow rating of the valve. The first stage is a small direct-acting relief valve, usually mounted as a crosshead on the main valve body, and includes a poppet, spring, and adjustable knob. The second stage handles full rated flow to the tank. The first stage controls and limits pilot pressure level in the main chamber. Relieving action through the main spool is as follows. As long as the system pressure is less than relieving pressure set on the control knob, pressure in the main spring chamber is the same as pump line pressure because there is no flow through the control orifice, and consequently there is no pressure drop from one side of the orifice to the other. When pump line pressure rises higher than the adjustment set on the control knob, the pilot relief poppet moves off its seat. This starts oil flow from the pump line through the orifice, across the pilot relief poppet, and to the tank. This restricted flow caused by the orifice creates a pressure difference between the pump line and the area across the pilot orifice. This pressure imbalance causes the main poppet to move off its seat. This will discharge enough of the pump flow to prevent any further rise in the pump line pressure. When pump line pressure drops below the control knob setting, the pilot relief closes, flow through the orifice ceases, and the main spring can reseat the main poppet.
Do y'all get how that works?
The pilot-operated pressure relief valve comprises a valve body, a main spool cartridge, and a pilot valve with a pressure setting adjustment. The pressure present in the primary port acts on the bottom of the main spool, and at the same time the pressure is fed to the spring-loaded side of the main spool via the control lines and containing orifices. The pressure is also present at the ball of the pilot valve. If the pressure increases to a level above the spring setting of the pilot valve, the ball opens against the spring. The pilot oil on the spring side of the main spool cartridge now flows into the spring chamber of the pilot valve and is directed internally to the secondary port and back to the tank. Due to the orifices in the control line between the primary port and the pilot valve, a pressure drop or pressure differential exists between the bottom of the main spool and the spring side of the main spool. This pressure differential lifts the main spool off its seat and connects the primary pressure port of the valve to the secondary or tank port. Fluid now flows to the tank, maintaining the set operating pressure of the valve.
I guess this is showing you what a hydraulic system would look like. That's not a trainer. Y'all, I never dealt with hydraulics, so like besides here, like I know hydraulics from here, but like I'm not a professional at hydraulics in the field.
I can guarantee you, I got no interest in hydraulics. That actually scares me.
Yeah, I'm scared of hydraulics, kind of.
Ever since that video y'all made me watch.
Getting the fluid underneath your skin.
Yeah.
Oh, yeah.
Yeah, that would suck.
That was super freaky.
A sequence valve is a normally closed pressure control valve that ensures that one operation will occur before another based on pressure.
Sequence valve.
In our clamp and drill system, we want the clamp cylinder to extend completely before the drill cylinder extends. To accomplish this, we place a sequence valve just before the drill cylinder. We set the valve to 500 psi. This will ensure that the drill will not extend before we have reached 500 psi on the clamp cylinder. Notice that once the drill cylinder has extended, pressure will continue to rise to the system relief setting of 1500 psi.
If you know, see this says 1500 psi. So if you know that once any amount of psi hits that clamp that it's going to push out, then if you set that at 500 psi, you can guarantee that that clamp is going to go out before that drill, right? And that's what the sequence valve is. Did you hear what he said about putting it right before the drill and setting it to a certain psi? It ain't got to be 500. Just let's just say 700 psi. So that's why it's called a sequence valve, because it allows something else to happen before that happens.
Forgot what the other symbol was right above the sequence valve. It was on the hydraulic trainer the other day.
That one?
Yeah. Was that the motor? No.
Hang on. That one right there. That would be the.
I think you're right.
I think so too, but the quick disconnect looks just like it as well.
I could be wrong.
No, I mean like it's probably a check valve, but are you confused, Houston? Do you want me to play it again so you can see it, like how it works? I'll restart it so you can see how it works.
No, I'm just so.
Like this is the sequence valve right here. That's the symbol for sequence valve, right? Okay. So what are you confused about?
So the top, all the way to the left, that's the motor, I'm guessing, right?
Yeah, that's the motor right there.
Okay, and then the high.
So let's figure out.
I'm just wondering how it gets.
The top is like a gauge.
Yeah, these are gauges. These up here are gauges.
Okay.
And basically when that gets pressurized enough to open up.
Yeah, this valve pressurizes, opens.
It's going to go to the clamp first because at that sequence valve, it has to hit 500 psi before it will open up to go to the drill.
Right.
So just the delay in having to hit 500 psi will cause the clamp to open up before the drill goes.
But would the top not hit before the bottom?
Yeah, the top would hit anyway.
Yeah, you want it to hit before the bottom.
Okay.
They wanted the clamp to do
more of a
it.
delay for the drill.
So like watch it, like they want the clamp to open before they want the drill to open, and watch it does.
System, we want the clamp cylinder to extend completely before the drill cylinder extends. To accomplish this, we place a sequence valve just before the drill cylinder. We set the valve to 500 psi. This will ensure that the drill will not extend before we have reached 500 psi on the clamp cylinder. Notice that once the drill cylinder
Yeah, it has to.
They just want the clamp to extend all the way out before the drill starts.
And would that not like entwine together? How that's going? Well, and you said that middle part, like right
Yeah,
there.
that's going back to the reservoir.
Yeah, that's what I would compare like
Excess.
yeah, that's just going back to the tank.
Alright.
And now it's like a complete circuit of flow now. Like that system will not stop until you turn it off or
Wire.
oh man. Alright.
There has extended, pressure will continue to rise to the system relief setting of 1500 psi. Valve is a normally open pressure control valve used to limit pressure in one or more legs of a hydraulic circuit. Reduced pressure results in a reduced force being generated. A pressure-reducing valve is the only pressure control valve that is normally open. A normally open pressure control valve has...
Every other valve would be normally closed. So a pressure-reducing valve is normally open.
Okay, I got a question.
What?
Because I know in electrical, normally closed means, you know, that's specific. In hydraulics, it would be opposite, right?
Yeah, that's what was confusing to me too. So, like, normally, with it being normally open,
I mean, it makes sense, though.
right, with it being normally open, it's allowing pressure to go through it until you close it. You get what I'm saying? So, like, with that reducing valve being normally open, it's not going to reduce any flow until you manually reduce it. So, I get what you're saying though. Like, it's kind of confusing to me too, because it's like you're trying to relate electrical to hydraulics.
That's the way it makes sense.
Yeah.
But it does make sense that normally open allows flow to come through.
Right.
But if you have like a wire,
and it's normally open, it's not
going
to create a circuit. Right. If you have like normally open contacts.
I mean, it makes sense.
Yeah, it's just like trying to wrap your head around it.
Because, like, everything we've learned up to this point has been all electrical.
And you have to kind of flip it to hydraulic, yeah.
Primary and secondary passages connected. Pressure at the bottom of the spool is sensed from the pilot line, which is connected to the secondary port. Remember, a pressure-reduced...
And it will show you, like, in the book, Houston, like, the only reason I'm singling you out is because Dylan's already done it. But like not in your book, like in this simulator book, you'll have a simulator book over there, and it will literally tell you which side. So like, it'll tell you which side the hose goes on, like what's your inlet and what's your outlet. So that's what it's saying, like what it just said about the pilot line with the inlet and outlet. It shows you in the book where to put that stuff. Like it literally says 1 and 2. It even says 1 and 2 on like the T-joints and the valves and stuff.
Yeah, don't get tripped out because on the cylinders it's got like a T built on it.
Yeah, and you'll figure out all that too. Once, like, it's hard to understand it. Like Dylan's probably understanding it a little bit better because he's already put his hands on it. Once you put your hands on it, it's not that hard. Like,
you'll get it.
Yeah, it's not that hard. So we're gonna finish out this video.
Reducing valve is normally open.
Questions, just stop me, okay?
Now, let's place our pressure-reducing valve in an actual circuit to see its application.
Now yeah, okay, this is good.
The illustrated clamp circuit requires that clamp cylinder B apply a lesser force than clamp cylinder A. A pressure-reducing valve placed just before the clamp cylinder B will allow flow to go to the cylinder until pressure reaches the setting of the valve. At this point, the valve begins to close off, limiting any further buildup of pressure. As fluid bleeds to the tank through the valve drain passage, pressure will begin to decay off and the valve will again open. The result is a reduced modulated pressure equal to the setting of the valve.
Do you understand how it's working?
A counterbalance valve is a normally closed pressure valve used with cylinders to counter a weight or potentially overrunning load. In this circuit, without a counterbalance valve, the load would fall uncontrolled or overrun, and pump flow would not be able to keep up. To avoid the uncontrolled operation, we place a counterbalance valve just after the cylinder. The pressure setting of the counterbalance valve is set slightly above the load-induced pressure of 1000 psi. This counters the load. As we extend the cylinder, pressure must slightly rise to drive the load down. Now that you understand the
The thing in the middle, is that what you're twisting up and down to let it through?
Talking about this right here? Yeah, that's the valve. That symbol just represents the counterbalance valve.
application of a counterbalance valve, push the extend and retract buttons to watch the function of the valve.
You might be confused now, but you won't be once you get on the hydraulic trainer, I promise, okay? Like, this is just going over, I'm trying to show you, like, a real life application of this instead of just reading it out of the book. You know what I mean? Like, I hate reading out of the book.
A brake valve is a normally closed pressure control valve with both direct and remote pilots connected simultaneously for its operation. This valve is frequently used with hydraulic motors for dynamic braking, because any downstream resistance will add to the load on the hydraulic motor. We pilot remotely using working pressure to keep the valve open during running. This eliminates back pressure on the motor. When we de-energize the directional valve, remote pilot pressure is lost, allowing the valve to close. The inertia of the load will now drive the valve open via the internal pilot, giving us dynamic braking. Now that you understand the application of a brake valve, push energize, then stop to see the valve function.
I'm not in control of this, guys. And it stopped. Yeah, it's about to be like 2 minutes from now.
I can't remember what that symbol is with the lines going down. What is that called again?
Which one?
The one like to the right. Yeah, like right above that with the lines.
That's
down.
just a pilot line, I think.
Okay.
But
I know it's a symbol for something because I saw it in there.
yeah. I'm not great with the symbols either.
I'm thinking, right, everything that's like a little dash like that is going to be pilot lines. Or drain lines.
I think it's at the very start.
I don't know if it's pilot lines or drain.
It might be drain line. An internal drain line, maybe. Yeah. Drain lines, that's the schematic symbol for it. A brake valve. Let's see. What I was trying to find was that brake valve definition. So it's a normally closed pressure control valve that prevents a hydraulic motor from running away or speeding out of control. A brake valve is both internal pilot lines and remote lines for controlling the speed of the motors in a hydraulic system. When pressure reaches the set value for the remote pilot line, the brake valve will open. Once the valve opens, the motor begins to rotate. If the motor begins running away, the pressure at the inlet side of the brake valve drops and the brake valve closes again. So that's what we just witnessed, that brake valve working. So when pressure reaches the set value for the remote pilot line, the brake valve will open. And let's see, once the valve opens, the motor begins to rotate. If the motor begins running away, the pressure at the inlet side of the brake valve drops and the brake valve closes again. So that's what we just watched, and I'm going to rewind it so we can understand what we just read. So, let's see. Alright, now watch them energize it again. See how it was, it opened? So, it's normally closed. And then it opened whenever, so I'm just trying to relate what you've read in the book to what you can see. So, when the pressure reaches set value for the remote pilot line, the brake valve will open. Once the valve opens, if the motor begins running away, the pressure at the inlet side of the brake valve drops and the brake valve closes again. So that will eventually close back if that was to happen. Do you understand that? Okay. Alright, we've watched that. So let's see if there's any more, or if they're just, oh, there's one with a cylinder. And this should be the last one of this.
Valve application is a good example of an unloading valve tank when the pressure at that location is a remotely piloted, normally closed pressure control valve that directs flow to the tank when the pressure at that location reaches a predetermined level. A high-low system is a good example of an unloading valve application. This system may consist of two pumps, one being a high-volume pump and the other being a low-volume pump. As the cylinder approaches the load, the pressure requirement is low. If the pressure requirement is below the unloading valve setting, both pumps work together to provide a rapid approach to the load. At this point, the system pressure increases, thereby opening the unloading valve. The flow from the high-volume pump is directed back to the tank at a minimal pressure. The low-volume pump continues to deliver flow for the higher pressure requirement of the work cycle. Once the flow from the high-volume pump is unloaded, both pumps join once again for a rapid return of the cylinder. The high-low system requires less input power to meet the work cycle's speed and force requirements. Now that you understand the application of the unloading valve, push the extend or the retract button to watch the function of the valve.
Did y'all understand that? Or do I need to replay it?
Which one is that?
Unloading valve. And let's see. Which was basically what we would see on the trainer as a check valve. We're looking at that right there.
Now that you understand the application of the unloading valve, push the extend or the retract button to watch the function of the valve.
Okay. And now watch when they retract it. You see it now? Okay. Cool. So, valves and all that are kind of confusing until you get on the trainer and look at them. But let's just continue going over these. Like, we're almost done. Like, I know your brain's probably fried at this point. But, so that's a monoblock mobile directional control valve. Some of these are a mouthful. Pressure compensated flow control valve, solenoid operated 2-position 3-way directional control valve. Now that's what we just watched, a check valve. Return line filter, ball valve, pressure gauge, temperature gauge, flow meter. That's what's above those tanks, right?
Right.
That's the symbol. Yeah, that's the symbol. Yeah, that's what I call it, a baseball too. That's what's above your like flow meter tanks or whatever. And that's when I was telling you, when you're like doing the needle valve and you reduce pressure over here, it makes the flow meter go up. But if you maximize pressure over here, it makes the flow meter go down, right? And it's easier to explain when you're looking at the trainer.
Flow meter's that tall.
Yeah, it's like the meters in the middle of the trainer.
I was thinking it was like a sack glass. You know those sack glasses with the line in the middle?
Yeah. Tachometer, quick disconnect. See, like a lot of these symbols look like crazy similar because, like, why did they use that and that? You know what I mean? Like, it's weird.
I feel like some of them, they use it because they use some components from this.
Yeah.
Internally.
Disconnect causes like a check valve, don't it?
Yeah.
Yeah, that's what I'm saying. It's just got that T on the end of it.
And it's flop.
Yeah. Safety bleed pressure connector, safety bleed return connector, reservoir, and that's it.
That was just the blue stuff down there, right? That just sat there in the reservoir.
Yeah, that's just like what I would consider that's what's called the tank on our, like that's just the tank where the oil is or whatever. I'm going to upload this to Canvas so you guys can go through there and study these. And then there's going to be like an open whatever test. And I'm going to do the same with the pumps. Like I'll make a quiz like on the different types of pumps. But it's not nothing to freak out about. Okay? And for like lab this week, what we're going to do is basically by the end of this week, I want everybody to be done with lab 6. So you would be 1 through 6. But it's not, when I tell you these activities, you would be on 0. But no, you're on 1. You just got to do 1, lab 1. But when
like I'm 6 labs behind.
No, but you're not the only one. But you got to understand, we're already a month into this class. So, but like the first one literally is this. So, one hose, and then you got 3 pressure gauges. That's it. So you've literally got 3 hoses, 3 pressure gauges. It's not hard. And once you get going, you're like, oh, dude, I wanna do it more advanced. So I'm gonna upload this, and let me stop recording.